Well, speaking of which, we ready? Where's everyone? I guess this is everyone.
Wow, there's a whole bunch of people out today.
Must be that cold front. All right, so last class we were talking about the hospital's rules, right? L'Hôpital's rule. And what it allowed us to do was take, anytime we saw the form of 0 over 0 or infinity over infinity, to use the rule to do limits again, right? And hopefully I illustrated some of its usefulness. All right, now what today is about is just extending on this, and we're going to look at some other versions of what we call indeterminate forms, and they're all right here, but I'm going to put them on the side of the board because I want to point to them while I'm lecturing. So this won't be on video, but at least you have them right here. And I want to talk about each of these forms before we start attacking the problems. These are called indeterminate because when you see something like 0 over 0, it means, of course, the top is headed to 0, the bottom is headed to 0, and you're trying to figure out if that ratio approaches something. Does it or does it not? One example of this is limit x approaches 0 of sine x over x. We know that you cannot just plug 0 into this. If you plug in 0, it is undefined at 0. But as you get closer and closer to 0, this does get closer and closer to something. It's equal to 1, right? That's what we have shown. Yes? So this is an indeterminate form. Anytime we see that, we had to do some algebra or some trick, right? But now we can also use L'Hôpital's rule. Infinity over infinity, same sort of thing. The numerator is growing, the denominator is growing. Does that go to a fixed number or not? Well, we can use L'Hôpital to help us figure that out. But there are a bunch of other indeterminate forms where we can also use L'Hôpital's rule. But as you'll see when we look at them, you can't use L'Hôpital's rule right off the bat. So let's take a look at the next example, which is anytime we get something like 0 times infinity. And it doesn't matter if that's positive or negative. So what you have here is a product, right? You have a product. And one of these numbers, or one of these expressions, is headed towards 0, right? Remember, this is in a limit. We're saying this is headed towards 0. This other one is headed towards infinity. There's a difference between that, right? Yes? If I said 0, I mean the number 0. That's one thing. I'm saying it's headed towards 0. Yes? Is that a question?
So when in a problem, it will specify the limit heading somewhere?
Yes. Let me give you an example of something like this. All right? Let's say we had the limit as x goes to infinity of 1 over x times e to the x. So what does this head to as x goes to infinity? 1 over a huge number, right, is going to get very small. So this is headed towards 0 times e raised to a big number. So we have to remember, exponential function looks like this. So as you go out to infinity, as x gets bigger, you're moving this way, and you're following the function, it's headed up towards infinity also, right? So this would go to infinity. Does that make sense? And the question will be today, and we'll do this problem in a minute, what is this limit? What is it? We'll figure it out. But the thing is, we can't just look at it and tell. This is an indeterminate form. Just like 0 over 0 was indeterminate, just like infinity over infinity was indeterminate, we will have to analyze this further.
Didn't have to do like a string before.
A what?
Didn't have to like multiply like I did in 1 to
That's what we were doing before L'Hôpital's rule, right? That's what we were trying to do. We're going to kind of throw that out now because L'Hôpital's rule's here to help us. Here's the problem though, and I hope you all recognize this. I said that you could use L'Hôpital's rule if you see this or this, right? You are not allowed to use L'Hôpital's rule if you see this here. You can't. It must look like 0 over 0 or infinity over infinity. And that goes back to the idea that you're going to do the derivative of the top and bottom, aren't you? That's what L'Hopital said, do derivative of top, derivative bottom. Here I don't have top and bottom, so I cannot use it yet. There's something I'll do, don't worry. We're going to be able to still use the rule, but not right off the bat. We have to mess with it a little bit.
Would it be like multiply that into that?
Let's wait, we'll see. Right now I want to focus on all your attention on all of these indeterminate forms. You need to know when you look at a limit when you actually have a problem. Are you okay there? These tables keep on like creeping closer. Do y'all want to like slide back so you're not trying to look around me? Yeah. So when you look at a limit, you need to know when you look at it, do you have a problem? You need to understand why you have a problem. Does everyone understand why this is indeterminate?
Yes.
Very small number times very big number. What is that? Well, it depends on how small that is, right? And it depends on how big that is. Right? And one of them is going to maybe outweigh the other. Who knows? We're going to have to figure that out. Now, another indeterminate form, now this one we have seen is infinity minus infinity. You've got a number that's getting really big. You're subtracting a number that's getting really big. Who wins? It's not 0. Okay, the answer to this is not 0. It will depend on the problem. How fast is that growing? How fast is that growing? When we did this previously, the technique we used was to try and get a common denominator, or to factor. But we'll address more of these today also. So that's indeterminate. The next one we have not looked at. We have never looked at this problem right here. Now let's first understand why it is indeterminate. If I gave you a number like, let's say 5, and I say raise to the 0, what would you tell me the answer is? 1, right? If I give you, 12 to the 0, you tell me the answer is 1. And you pretty much have been told your whole life that anything to the 0 should be 1, right? So this raising it to the 0 wants to turn it into a 1. The problem is that you've also been told that 0 squared is 0, and 0 to the 10th power is 0, and 0 to any power is 0, right? So the base is like, hey, I want to be 0, right? I'm getting closer and closer to 0. I really would love to be 0. And if you raise that to any power, it should still be 0. But then the power, the exponent power says, hey, look, when I raise things to my power to 0, I want to turn you into a 1. Do you see that? It's like two forces fighting each other there. And so, yeah? No? Yes or no? Yes? Okay, so this is indeterminate. Something's getting small, something's getting small as an exponent. Here's a specific example. Limit x goes to 0 of x to the x. See, the base is getting small, right? As x goes to 0, the base is getting small, but the exponent's also going to 0, so you get that battle. Who wins? With me? Okay. The next one, infinity to the 0. That's very similar to the one we just looked at. Anything to the 0 should want to be a 1, right? But infinity raised to, if I get a huge number, right? Huge number, and I raise it to a power, it should still be a huge number? What do you think? Remember, this number is not 0, right? This number obviously can never be infinity, but if I take a huge number, those are all zeros. Okay, and I raise that to a small number, 0.00001. That's probably going to be pretty big still. Because I have a lot more, this number is a lot bigger than that one out there, right? Now you could say that that one's pretty small and that one's pretty big. So if I make this one smaller, maybe this will get smaller. But what happens if that's getting bigger and bigger while that one's getting smaller and smaller? Like, who wins that battle? You understand that? This is fundamental that you understand that there's like a tug of war going on here. The next one, 1 to the infinity. So you have something that's trying to become a 1 versus something that's trying to raise it to a bigger power. there. What happens is x goes to, no, make that cosine x, sorry. What's cosine of 0? 1. So this is trying to become a 1, right? 1 raised to any power should be 1, right? 1 squared is 1, 1 to the 100th power is 1. So if it could ever get to 1, then the power wouldn't matter, right? If it actually got to 1, it wouldn't matter. But see, the thing is, it's not going to ever get to 1. It's approaching 1. So this guy's trying to become 1. And then this right here is infinity. Because you have what? Fixed number over 0. Fixed over 0 we studied already. There was one of 3 answers. Infinity, negative infinity, or does not exist. This one would be positive infinity because the numerator and denominator are both always positive. 1's positive, x squared's positive, the ratio of 2 positive numbers is positive. Fixed on top, number on the bottom gets small, ratio gets big. Understand? So this guy on the bottom is like, hey, I want to become 1. Please let me become 1. And the power's sitting there like, you're not 1. I'm just going to keep raising you to bigger powers. Like, no, I'm not going to let you get to 1. Right? I'm going to make you bigger or bigger. There's going to be that battle. Understand? I'm getting that glary look.
Are these indeterminates determined by union or by law?
No, this is just, these are the forms that happen in calculus that happen, that we see that we need to address. Now, there are things that are not indeterminate that we can find the answer without doing any calculus, and we don't want to confuse them. A lot of students sometimes just think that if I can just put infinity and 0 together in any way, it's always indeterminate form. But that's not the case. Look at the first one over there. If I take the limit and I get 0 over fixed, what's my answer? What's that? So what happens on top? You get 0 on top, you get 2 on the bottom, right? So this is headed to 0 over 2, the answer is 0. That's not a problem. The answer would be 0. So this fixed, 0 over fixed is never an issue for us. If we flip it over and we get fixed over 0, that was not a problem really. I mean, we did have to look at it, but this was the one where we had 3 options, right? It was either infinity, negative infinity, or does not exist. We studied those. But this would not qualify for L'Hopital's rule because it's something we can do without L'Hopital's rule pretty easily. 0 over infinity. That is not an indeterminate form. Limit. X goes to infinity of, let's do this, e to the x, and on the top, let's put 1 over x. I'm just trying to illustrate what's happening here. So the numerator, I'll say that part right there, is trying to turn into what? 0. So it's getting smaller, right? The denominator is headed to infinity. So if I take a small number and divide it by a big number, what happens?
0.
It gets smaller, right? So it's like this one's like, hey, I want to become 0. And this one's like, I'm here to help you, right? I'm here to help. I'm going to divide you and by a big number. It's going to help that get even smaller. Make sense? There's no battle there. The answer is what? 0, okay? What's the next one? Infinity over 0? Wait, that's,
Yeah.
okay, infinity over 0. So the top is like, hey, I want to become infinite, right? And the bottom's going to do what?
Approach 0.
It's going to approach 0. Let me give you an example of this. Limit, I'll just take the one we just had and flip it over. That's the same problem flipped over. So we have a number up here, it's getting big, right? This numerator is getting huge. And then what happens if you divide a number by a small number? It gets bigger, right? If I take the number 2, divide it by 1/2, that's really 4. If I take the number 2 and divide it by 1/4, that's really 8. If I take the number 2 and divide it by 1/8, that's really 16. So if the top isn't changing and the bottom's getting smaller, the ratio gets bigger. So the answers get bigger and bigger and bigger, right? But this is even better, because the top's getting bigger too, which helps it get bigger faster. Make sense? That's not a problem. 0 times 0 is not a problem. One number wants to get really small, the other one's going to get really small, and when you multiply two really small numbers together, they get even smaller. Do you believe that? If I take a small number, like 1/100th, and I multiply it by another number that's really small, 1/1000th, the answer is 1 what? 100,000, because you multiply straight across, right? Bless you. This number is even smaller than both of these, right? So they help each other out. They get smaller together fast. Infinity times infinity. Most students have no problem with this. Numbers getting big times another big number. Two big numbers multiplied together should be big. So that's not a problem. The answer to that is infinity. I didn't put the answer to this, did I? 0 times 0, that's obviously 0. Infinity times infinity. How about infinity plus infinity? Infinity. You're adding two big numbers together, still going to be big. 0 to the 1. Wait a minute. Yeah, 0 to the 1. So 0 to any power should be 0, right? And anything raised to the 1 should be itself. So this guy's like, I would love to be 0, right? I want to be 0, I want to be 0. And the exponent stood in the number there going, look, I'm going to let you be what you want to be, right? That's what I do. I let you be whatever you are. And so this will be 0, right? Not a problem. An example of this one would be limit x goes to 0 of, let's say, sine x to the x. No, that's not. That's not it at all. Hold on. Let me do this. I'll do sine x to the cosine x. That'll work. Because they really want me to renew. All right. As x goes to 0, sine of 0 is 0. So the base wants to be 0. Cosine of 0 is 1. And so that falls into that format. This should just go to 0. No work has to be done. Do you see how people can sometimes get these confused with these without like thinking through, like, do you even have a problem or do you not, right? What else? 1 to the 0. The base is sitting there going, I'd really like to be 1, right? 1 to any power should be 1. And then the exponent's like, hey, I'm sitting here, I'm 0, right? Anything to the 0, it's going to turn it into a 1. So they're helping each other out. Yeah? Infinity to the infinity, is that obvious? That's just a big number raised to a big number. That should still be a really big number. So that should be infinite. This last one's a little tricky. People have trouble sometimes with this last one. What do you think? I'm telling you that that is not indeterminate, that you can figure out what that is. Should be 0. That's headed to 0. Now let's talk about why. If your base is getting smaller, let me do this. Limit as x goes to infinity of 1 over x to the x. That's what we have there, something like that. So imagine that you start letting x get big. So let's just try, let's plug in a big number for x, like 100. This would be 1 over 100 to the 100th power, wouldn't it? When I multiply 1 over 100 times itself 100 times, that's going to be an extremely small number, isn't it? Because it's 1 over 100 times 1 over 100 times 1 over 100. So I'm going to have 100 hundreds multiplied together on the bottom. 1 divided by that, that's infinitesimally small, right? So this is really wanting to become 0. And if I go further out, then it's going to be an even smaller number raised to an even bigger number. You're going to have more of these fractions, and each one of them is smaller, and it gets small fast, right? So this should head to what? 0. Okay? All right. So our goal now is to look at these types of forms, be careful for those. If we see those, we're just going to be done. We're going to just work them out and we're done. But we're going to be working on those, and we're going to be trying to do them with L'Hopital's rule instead of with that hard algebra stuff. Y'all ready? All right, let's do it. So the way I planned on doing this, the homework assignment for this section, I've completed the homework assignment. I put it online. The solutions are up. So I'm going to work all the problems I did not assign for homework. That's what I'm going to do. And after I'm done, I will have done every limit problem in this section. All right? So I'm going to start with number 2. Number 2 is the limit. I have not worked these out, okay? Before I came to class, I did not work these out. So I do not know what we're going to face here, which is probably a good thing, right? Okay, let's talk about this limit. Just like every other limit, we always want to just first do a direct substitution and see what happens. So if I plug in 2 here, I get 4 plus 2 is 6. Minus 6 on the top, I get 0. So I'm going to put here a little arrow showing the form I'm getting, 0 on top,
0, 0.
and then 0 on the bottom. This is bad, right? This is an indeterminate form, so I have to do something. I can use L'Hopital's rule because this does look like 0 over 0. So I'm going to go straight to L'Hopital right now. I'm going to take the limit as x approaches 2. And then L'Hopital's rule says all I have to do now is take the derivative of the top and divide it by the derivative of the bottom. 2x plus 1 on top is the derivative. And then derivative of the bottom, 1. And then I just take the limit again, right? If I take the limit again, I get 5 over 1. So the answer is 5. So remember what this means. If I were to draw this function, right? If I were to draw it, then when I get to 2, the function is undefined. Totally undefined. But as I approach 2, from both sides, the function's value is approaching 5. So from the left and from the right, my function does that. I have a hole at 2, but I've got something as I come in from both sides. Understand? Okay. Now, I'm sure deep inside you just want me to give you like 30 of those problems on your test, right? Just like that. Just polynomial over a polynomial, derivative, done.
It'd be so nice.
Yeah.
It would be really nice. What would you like for Christmas? Well, Matt, you told me there has to be a large sum in my Swiss account. My offshore account.
Yeah.
I was like, you have one of those? He goes, yeah.
Number 6. Anybody else need to turn in the assignment from last time? There apparently was a mistake on one of them. Number 13? There's something about a negative? Okay. Anyone else?
I have to even write it down. I was thinking,
But I didn't do number 13. I didn't know there was a question.
It's not the end of the world. You'll be fine.
Did you open a box on the answers?
No. Fine.
I wrote it on the back of my notes. Can I rewrite it?
You can. I mean, you can turn it in. I can't guarantee you. I want you to focus on this right now. I just don't want you doing it during class. Do it later and then we'll talk. All right, what about here? X is going to 0. Numerator is headed to 0, and the denominator, cosine of 0, is 1. Right? So 1 minus 1 is 0. So go ahead, you try L'Hopital on it real quick, and then I'll work it through, and then we'll see if we get the same thing. Also make sure you do a little L or a little H over here, your preference. What's the derivative of the bottom?
Negative sine x, but there's a minus, so positive sine.
Positive sine x. What happens if you try to do the limit again? You get 0 over 0 again, don't you? And did I tell you what happens now? If this happens last class? You can do it again. You can do it as long as you have 0 over 0 or infinity over infinity. You can keep repeating L'Hopital's rule as many times as you need to. So I'm going to apply L'Hopital again. And I get 2 over cosine x. And now if I let x go to 0, what do I get? 2 over 1. Which is 2. So again, if I were to draw this function, if I were to graph it, at 0 it would be undefined, but I could tell you that it's approaching 2. As I get closer to 0, it's getting closer to 2. We good? Now I'm going to do a pretty big jump here, and we're going from number 6 to number 12, so I'm anticipating more of a challenge. Let's see. Limit, they're going to use t instead of x. All right, well, we can handle that. 8 to the t minus 5 to the t over t. First, do your direct substitution. T is going to 0. What is 8 to the 0? 1. 5 to the 0. 1. 1 minus 1. 0, so the top's headed towards 0. Bottom, that's just 0. Okay? 0 over 0. Good. We can use L'Hopital. Limit. T goes to 0. Derivative time. The bottom's easy, right? Derivative of t is 1. We're differentiating with respect to t because t is the variable, right? So how about the top, though? What's the derivative of 8 raised to the t? 8 raised to the t. ln, good. ln 8. ln 8. Natural log of 8. Remember, that goes back to this formula. Derivative of a to the x is a to the x ln a. That was the formula when we did exponential functions. All right, that's the derivative of this. Then I still have what? Oh, yeah, derivative of t would be 1. So I can move on to this one? Okay, so this one derivative is 5 to the t times natural log 5, right? Questions? Let's let t go to 0. What's 8 to the 0? 1. 1 times natural log of 8 is natural log of 8. Minus 5 to the 0. 1 times natural log of 5. It's natural log of 5, right? So the top is headed towards natural log of 8 minus natural log of 5, and the bottom is just 1. So that's the answer.
You want exact answers?
Yes, we'll leave it exact. But that's not what will be in the back of the book. That's what will be in the back of the book. So you see what they do?
They just condensed the logs.
They condensed the logs. They took the 2 logs with subtraction, turned it into a single log with division.
Which do you prefer?
This. I prefer that because that just shows you know that property. You know, it's that you understand the property. All right. So far, things are running pretty smooth. Would you agree? Pretty smooth? As long as you can do derivatives, you're in business. Let's go to 18. I'm hoping that on one of these I'm going to have to scratch my head. I'm hoping that's going to happen here. 18. Limit x goes to 0. This one just looks worse. X over arctangent of 4x. Right. I think this is where things start getting, we start getting into some murky waters. Because if I ask you, like, what's cosine of 0? Everyone's like 1. If I say what's sine of 0, everyone's like 0, right? When I start asking you what like arctangent of 0 is, that's where people start to waver a little bit. So let's see if we can get our heads around this. X goes, is it? I don't know, is it?
It is 0.
Let's see. X goes to 0. X goes to 0, and you get 0 on top, right? See, 0 on top by itself doesn't tell us anything, right? Because it could be this, it could be this, it could be this, right? So it could be, not indeterminate, it could be indeterminate. I need to figure out what the bottom's doing. What you don't want to do is just start doing L'Hopital. Just start, just start doing L'Hopital. That's going to get you in trouble. All right, I'm going to plug in 0 here. I need to figure out what arctangent of 0 is. According to the calculator, it's 0, so the answer is 0. What does this really mean? This means tangent of what angle? I'm going to call it theta. Tangent of what angle equals 0? In other words, where on the tangent function does it spit out 0? See the tangent curve, this is the tangent curve. I'm saying where's the y value 0, right? This is like the x value, what you plug in, this is what comes out. So where's your output 0? And that's going to be your up and down, that's going to happen right here, that happens at 0. Right? So the bottom goes to 0 also. Now while we're talking about this, what would arctangent of 1 be? Pi over 4. So this is asking where is your tangent function 1? What angle gives you that? And for that answer, I would not draw that. What I would draw instead is the unit circle and then say at what angle, right? At what angle here, what theta, question mark, is tangent 1? Tangent by definition is the y coordinate divided by the x coordinate. Do you all remember that? And so the only way I'm going to get a 1 is if the y and the x coordinate are the same. And that happens at 45 degrees, which is pi over 4. Now, if you did your homework from last section, if you did, then you had to do this, the first 8 problems or so, where it was all about this. So we need it here today. All right, back to this. We have 0 over 0, which means we can do what? L'Hopital. L'Hopital. Derivative of the top, 1. Derivative of the bottom. And that's going to be some chain rule, isn't it? Derivative arctangent of something is 1 over 1 plus that something squared, right? Am I done? Times the derivative of what's in there, which is 4. Agreed? Let's go ahead and let x go to 0 and see if good things happen or not. If x goes to 0, we get 1 over 1 plus, that's 0 squared, but then I have times 4. This is just 1 over 1 is 1, this whole thing times 4. So you just get 1/4, don't you? Yeah. 1/4? 1 over 4. What do you think? So far, okay? We haven't moved from this one, have we? We've had this every time. We need some of this, don't we? Okay. I have a feeling it's coming. Number 20. Limit x goes to 0 of e to the x minus e to the negative x minus 2x over x minus sine x. What happens as x goes to 0 here? So e to the 0 is 1, right? I'm going to write this down. There's a lot of stuff here. 1 minus e to the 0 again, right? Negative 0 is the same as 0, right? So e to the 0 again is 1 minus 2 times 0, which is, again, just 0. So the numerator is headed towards 0, isn't it? Denominator. 0, take away sine of 0 is 0. So 0 take away 0, this is 0. 0 over 0. It's somewhat disappointing. I was hoping it would be something else, but it's okay. L'Hopital? Take a second to take the derivative. See if you get the derivative right. Is this what you got? Derivative of e to the x is itself. Derivative of e to the negative x, you have to pay attention to that one, don't you? Because you have e to the negative x. When you take the derivative, it's itself, but then you have to take derivative of what's up here. The derivative of that is negative 1. But it was already being subtracted. So when you put the negative and the minus together, you get the plus. Do y'all see that? And then the derivative of negative 2x is just negative 2. On the bottom, I think that's pretty straightforward. Derivative of x is 1, derivative of sine is cosine. But now when you try and plug in x is 0, you're getting what? What are you getting?
Fixed over 0.
Is it fixed?
Yeah. 1 plus 1. Oh, no, it's 0.
It's 0 still, isn't it?
No, it's 0.
You're still getting 0 over 0. Right? Because look, if you let x go to 0, e to the 0 is 1. Right, so you get 1 on top there, plus e to the 0 again is 1, minus 2 over 1 minus cosine of 0 is 1. So you get to do it again. I would just like shake L'Hopital's hand. I'd just be like, thank you. That's what I would do. Thank you. I'd probably pat him on the shoulder. God, man. Awesome. Okay, derivative. E to the x, then what? Minus e to the x this time. Because again, you have to do chain rule on that again. You'll get another negative to pop out, but then it's plus and minus is going to be minus. And then derivative of negative 2? 0, so I don't have that anymore. On the bottom, oh, crap.
It's supposed to be addition.
Pardon me?
It's supposed to be addition.
Where?
It's supposed to be e to the x plus e to the x.
Where, here? No, that's what I'm saying. What happens when you take derivative of this? It's itself times the derivative of what's up here. What's up here? What's the derivative of what's up here? Negative 1. So that negative 1 is going to come out and become a minus out here. You see that? That's why when we took the derivative of this, it gave us a plus. What's the derivative of the bottom? Sine x. Right? Sine x. Uh-oh. I'm getting 0 over 0 again. Next one I'll get it on, right? The next one I'm going to get on. Can you kind of see what's happening here? As you go through and you start taking these derivatives, your denominator, right, is kind of getting cleaner, right? It went from x minus sine x to 1 minus cosine x. The next time through it's just sine x. And you know that if you plug in 0, you're going to get 0 here. But the next derivative through, that bottom's going to be what? Cosine x. That's going to go to 1. And that'll be a good thing. So one more L'Hopital. What is the derivative of the top here?
Plus
E to the x plus e to the negative x over cosine x.
which is 2
Yeah. Now e to the 0, 1 plus e to the 0, 1 over 1. The answer is 2.
Is there a shortcut to that, or just
What?
I feel like there's a pattern we missed.
This is the shortcut. This is why I want to shake L'Hopital's hand. Because I can't even imagine trying to do that limit without L'Hopital's rule. I can't even imagine what algebra I would do to that to make this thing come out. Is it possible? I'm just going to say I don't know. I can't look at that and see the algebra that I would do. I would look at that and I would think L'Hopital. That's a really powerful rule. I was talking to one of my colleagues about this before I came into class today. And this particular colleague, who will remain unnamed, he goes about proving most of the theorems in his calculus courses. And so he keeps it as a pretty rigorous class. And I asked him if he proved the L'Hopital's rule. And he said no. And the reason why is because the proof is very, very, very tough. It's not something easy. I remember when I had to prove it when I was in school. We had to do it in a course called Real Analysis, which is like a junior level course, math course. We had to prove L'Hopital's rule, and I just remember I struggled with it for quite some time. Several weeks before I actually understood the proof. So it's not something I can just throw up on the board, kind of like I did when I proved the product rule. There was a hidden 0 in there, and I was able to show it to you. This one's not easy to prove. I wish I could, because man, it's such an awesome rule. But when you think about what it says, it doesn't seem intuitive. Have y'all even thought about what the rule is saying?
That the derivative divided by the derivative.
It's saying that if you have a ratio of two functions, right? And if that thing's headed to 0 over 0, or infinity over infinity, let's just look at the 0 over 0. That means that the top's headed to 0 and the bottom's headed to 0. Let me graph for you two functions. Robert, get back on track. Okay, I'll just do it. I'm just going to graph two arbitrary functions. That's f. I'm going to graph some other arbitrary function. That's g. And do you agree that as I approach, let's say in this case, 0, do you agree that these are both approaching 0?
Yes.
As I approach 0, they're both approaching 0. The ratio of the two functions means if I take how high this, f's on the other side. If I take the height of f and divide it by g, so whatever that number is, f, divided by that number g, right? That's the ratio. And start to move closer to 0, you see that I'm just dividing those two numbers together? And I'm trying to figure out what that ratio is headed towards. So get closer and closer, divide those two numbers. Divide those two numbers. Divide those two numbers. Each one of them individually is headed to 0, but I'm interested in their ratio. Somehow, amazingly, it's equivalent to the ratio of what? This is equal to the ratio, limit, whatever, of the ratio of their what? Derivatives. That means if I take the slope of the tangent line here and the slope of the tangent line here, that ratio is the same as the ratio of the heights of the functions. What? It just doesn't seem that it would be that way. It seems like you could draw functions that wouldn't behave that way. But it turns out that the ratio of the tangent lines is equivalent to the ratio of the functions. And that's just strange to me. That's always been awkward. That's why I want to send them over to your house to do some calculus with you. Lock yourselves in the room there and can drink it up. All right, sorry, get back on track here. All right, this one looks pretty nasty. Limit x 22, sorry, 22. Limit x approaches a from the right of cosine x times natural log of x minus a over natural log of e to the x minus e to the a. Oh my goodness. That looks real bad. Oh, we definitely have to figure out what's going on here. So everyone, let's let x go to a. Let x go to a, and I'm going to do this in a little detail here. We will have cosine of a, right? That's what happens as x becomes a, times natural log of a minus a, right? Over natural log of e to the a minus e to the a. You follow? I've just replaced all my x's with a's. Now, there is a reason why we are approaching a from the right here. And it has to do with the fact that I'm about to try and take natural log of this. This is 0, isn't it? But I'm approaching a from the right, which means that this number is always a little bigger than a, isn't it? To the right of a, it's a little bigger. So when I take a number that's a little bigger than a, right, that x right there, that's a little bit bigger than a, and I subtract a, is that going to be positive or negative? Positive. That's important, because what if I came in from this side? Then this difference would be negative, and that would be undefined because natural log is not defined for negative numbers. So we have to throw the plus on there so that the limit makes sense. Understand? Now, but it doesn't change the fact that I still have something pretty crappy going on here. A minus a is 0, so this in here is headed towards 0, isn't it? And e to the a minus e to the a is also headed towards 0. It's not 0 over 0. What is natural log of 0? Go back and look at the natural log function. This is what natural log looks like, right? At 0, it's undefined, right? At 0, it's undefined. But I'm in a limit right now. I'm approaching a from the right, which means this difference is approaching 0, right? Which means I want to know what happens to the natural log function as I approach 0. What does it do? It goes to negative infinity. Do y'all see that? All of this together goes to negative infinity. Yeah? Same with this. This goes to what? Natural log of something that's headed towards 0 also goes to negative infinity. What about the cosine a? You have to at least consider it. What is cosine of a? It's some number. And that doesn't have any effect on anything. It's some number. right? So this is negative infinity over negative infinity. Is that an indeterminate form? Yes. It's this one right here. It's infinity over infinity. By the way, I should add this. On this infinity over infinity, it does not matter if you have plus or minus. You can have positive infinity over negative infinity over positive infinity, negative over negative, positive over positive. All of them are indeterminate. All right, well, we've got our work cut out for us then, don't we? We've got to take a derivative. Because this is infinity over infinity. We can use L'Hopital's rule. So at least we're happy about that, right?
Oh, yeah.
Yes. Here it comes. X approaches A from the right. And I'm going to erase all this. Can I erase all this? It's just... All right. So I have to take derivative of the top. And I did here, yes, product rule. We have to use the product rule. Right there. Why don't I have to do the quotient rule? This is a quotient. Why don't I have to do the quotient rule? This is L'Hopital's rule, right? We don't want to confuse it with taking derivative of a quotient. L'Hopital allows us to focus on the top and bottom separately. But when we look at the top, if it's a product, we got to do the product. So I'm going to do derivative of the top, derivative of the first one, which is negative sine x times the ln x minus a plus, now the derivative of ln of x minus a. Remember, a is a constant. X is your variable, right? A is a constant, x is your variable. What is the derivative of natural log of something? 1 over that something. Times the derivative of what's in here, which is just 1. Because the derivative of x is 1, and the derivative of a is 0. And then finish off the product rule, cosine x. Oh, man, okay. Now the derivative of the bottom. The derivative of natural log of something is 1 over that something. That's a mistake. 1 over that something times the derivative of what was in here. Now be careful here. What's the derivative of what's in here?
E to the x minus e to the x times 1 times the minus e to the a. What's the derivative of a, which is a constant? So 1 is 0.
I'm hearing the correct and incorrect answers. So let's go piece by piece. What's the derivative of e to the x? Itself, okay? I'll put this in parentheses because I'm going to have 2 pieces, or maybe I'm not. Minus, what's the derivative of e to the a?
0.
Just 0. Just 0. Why? A is a constant, right? E to a constant, that's like me saying e squared. What's e squared? I don't know, a number, right? Whatever it is. E to the a is a constant. So the derivative of it is 0. So this should be minus 0. Do I really need to write minus 0 there? No. So the derivative of the inside of this natural log is just e to the x. All right. I don't know if I'm going to get it. I don't know if I'm going to be able to get away with this or not. As far as like, am I going to be able to do anything with this?
Well, you can slide that and kind of clean it up.
This looks like a disaster, to tell you the truth.
I mean, you can at least kind of clean it up, right?
Let me, before I clean, let me just see if I can let x go to a and maybe I'll get lucky. If x goes to a, what happens? Negative sine of a. Some number. Oh, crap. Natural log of a minus a. A minus a, 0, natural log of 0. That goes to negative infinity again. So I have maybe a little bit of a problem there. This is going to negative infinity. Do you agree? Times a number. Oh, crap. Okay, so 1 over a minus a. A minus a. That's going to 0. Fixed over 0. is not indeterminate.
Is there
That's either infinity, negative infinity, or does not exist, right?
positive infinity?
Cosine of A,
Some number.
some number, right?
Wait, so is that positive infinity? Yeah, right.
I don't know yet. I'm just thinking this through. I know this is a number. I know this is going to negative infinity. I know this is either going to negative infinity or positive infinity or does not exist. I know that's going. Oh, we'll go to positive. I'm just not. I didn't want to like get into the fine details of it. But yes, it will because that A right there is a little bigger than A. That minus A, it'll be a little positive small number. Yes, but I'm just kind of thinking through it, right? And then down here, what e to the A minus e to the A. 0 fixed over 0. One of the three things that could happen again, right? Fixed over 0 times e to the A, which is just a number. Yes.
What is that e to the x go on the bottom? Because it's the second part. Like it would be the log a of x equals 1 over x ln of a.
1 over x.
ln of a being e to the x, right?
No. The derivative of natural log of something is just 1 over that something.
Yeah.
But you don't have the little ln a there. That's if you had log base a of something. Then you would say this is 1 over that something ln a. But if it's natural log, we don't have this piece. All right, so this is going to be a mess, right? Wow, I do not like this problem. Do y'all see?
You said that there was going to be a problem that you had to scratch the head.
I was hoping that I would get something exactly like this. Yes.
When you get two indeterminate forms, you get one on top of one. Well, I mean, you get infinity, negative infinity plus an infinity on top, and then you have your infinity on bottom.
Which in the end of the day really just turns out to probably just be an infinity over an infinity. Which maybe I can still do L'Hopital's rule again. But do you feel like taking derivative of that again?
Do we have much choice?
We may not. So let me try and do what I would expect you to do at this point, which is to clean it up. Algebraically, let's see if we can just clean this up, make it look a little nicer, okay? So I'm not doing anything right now but cleaning up. All right, so here's what I would do. I'm still going to be trying to do the limit of this, right? So I'm going to put the limit here. I'm just going to write negative sine x times natural log of x minus a, all right, plus cosine x over x minus a over e to the x over e to the x minus e to the a. So all I did there was slid the cosine on top, slid the e to the x on top, right? That's it. And the next thing I'm going to do is remember that this is kind of like a fraction over a fraction. And I can flip this up. You all understand? Do that next. No promises that I'm headed in a good direction, all right? So that's why I said I didn't work these problems out. I wanted to have a problem like this where you're actually seeing like the process that I would go through so that you kind of understand. It's not always just going to be smooth sailing the whole time. Was there a question?
Yeah, I don't know if
Yep.
it's a stupid question. That natural log of x minus a, what if you were to switch that around to natural log and x over a using the logarithm?
You can't, because the property we have for log says this. Natural log of x over y is natural log of x minus natural log of y. If you have subtraction between two logs, you can turn it into a single log with division. But if you have subtraction in a single log, you cannot turn that into anything. It's stuck, unfortunately. All right, so I'm going to try this. I'm not feeling good about it, but let's multiply through. Get rid of this, and I'm going to multiply this top by the reciprocal, which is